Hi, welcome back. So today we will continue on the topic of differential amplifier. So we're just gonna cover the DC transfer characteristic for today. So let's get to it.
Don't worry, y'all. This one will be a very quick one. So we will continue the differential amplifier on DC transfer characteristic. Previously, what did we learn? We examined the BJT differential pair. So in this differential pair, we assume that Q1 and Q2 are identical. That means beta 1 and beta 2 are equal. We also understand that when the two input VB1 and VB2 are equal, the circuit becomes symmetrical. That means the current IQ got slipped equally between two branches, therefore making the difference between VC2 and VC1 to be 0. But how does the differential pair behave when we actually introduce a difference between the two input VB1 and VB2? Last time we analyzed that difference qualitatively with a value called delta I. So when we introduce the difference in the input, this current changed by a small amount delta I current. And this time we will try to be more analytical about that delta I. So let's say the goal now, the question is how does the collector current change with respect to the change in the two input? I mean, with respect to the difference between the two input. So how can we derive an expression to relate IC1 and IC2 to VD, and VD is divided by VB1 minus VB2. So first, what do we know about the collector current? This is back in chapter 5, I believe. You can have an exponential relationship between VBE and IC, okay, where IS is the coefficient and VT is dependent on temperature, so at RT is 0.026. So therefore, you can have an expression of IC1 and IC2 based on VBE1 and VBE2. If we neglect the base current, okay, we can estimate that IE will be equal to IC. So emitter current will equal to a collector current. So this current here will be equal to this current here. Therefore, the constant current source IQ, which is slit between IE1 and IE2, can be assumed to be a slit to IC1 and IC2 also. So here the equation, I can have IQ equal to IE1 plus IE2, and I can make it equal to IC1 plus IC2. Now what next is basically I can plug in this equation, these two equations now. Then I can have IS multiplied by exponential of VBE over VBE1 over VT plus another IS multiplied by exponential terms of VBE2 over VT. So if I divide IC1 in this equation for the IQ equation, here I can have a ratio of IC1 over IQ. After I simplify on the terms, I'll have this. Now I will do the same thing for IC2. So I divide IC2 for IQ. I simplify all the term, I have this. Now I can also define that VD equal VBE1 minus VBE2. Some of you may ask, why so? And as the main difference between these two voltages are actually introduced by the difference between these two voltages. So you can divide it's like that. So now you can actually plug VD back into here. So this term will become minus VD. So you can have basically IC1 equal to IQ divided by 1 plus exponential of minus VD over VT. And for IC2 is similar terms, but here you have a plus sign for VD. Okay, forgot to do the animation there, but excuse me on that. So what did we learn so far? Okay, so we have this expression here, right? Okay, and now if you look at this expression, the general form is you have a constant over 1 plus some variable. This is why I give you this plot. This is the general plot I put on MATLAB. I have it plot out the equation of 1 over, the expression of 1 over 1 plus exponential of x. So in this plot here, you can see that if VD is 0, that means the x term is 0 for both, right? So if the x term is 0, then this whole term will be equal 1/2. Therefore, you can see that now our current IC1 and IC2 will be 1/2 IQ. This implies that when there's no difference, the current IQ here is split equally to both transistors. Okay. Now what if I introduce some differences? So the first difference I introduce, like the first thing I try to examine is what if I have VB1 is larger than VB2, so this voltage larger than this voltage. If that happen, then I will have a positive VD, right? If I have a positive VD, so this term will be go to the negative side, right? It's a positive, so negative of a positive is negative. So this term will be positive side, and you can see IC now IC will become have a negative x here. So the whole term will go toward 1. Y for IC2, the whole term will go to 0. Okay, so what did I see there? I can see that uh, basically if I have more voltage here, there will be more current flowing here. So likewise, if I have more voltage here, I will have more current flowing here. Okay, so if you look at this plot here, for a small range, actually you can use some linear estimation, right? So for a small range, you can linear estimate the relationship between that distribution of current between two branches. However, if VD is too large, or either on the positive side or the negative side, so if VD go over too much on this way or this way, what happened is now your current will only go to one single transistor and turn up another one. Okay, so as you can see, this is another plot that represent, this is the plot for ICQ, this is the normalized plot for IC1, and this is the normalized plot for IC2. There's another example in the textbook called example 11.2. I recommend you should go through it if you have some time. Then in that example, you can go over the linear estimation also when VD is close to 0. Okay, now we can consider some small signal parameter. So now in this circuit, um, if you already go over the example 11.2, you would probably know what is the forward transconductance parameter, GF. But if you have not, it's basically defined as the slope of the IC-VD curve when the value of VD is close to 0. Therefore, you can basically calculate VD as IQ over 4VT. Okay. Um, Now you can relate your GF, which is forward transconductance, uh, to the transistor conductance GM, and that relationship can be shown in here. So GF basically is half of GM, and this is also assuming that this IQ here, okay, this half IQ is actually equal to this value half IQ is equal to the collector quenching point, no, the quenching collector current of either transistor Q1 or transistor Q2. So now you have all of the background information that you need. Now let's ask a question. How can I find the voltage gain? Because you remember the main function of this differential pair amplifier or this differential amplifier is that you find the difference between your two input, then you amplify that difference up. So how can I find the voltage gain to amplify that difference? So we use the same method that we do. We start with the output. We just have to relate that back to VD, which is our difference. So if we define our output as VC2 minus VC1, okay, and we can calculate VC2, for example, by just this is our voltage loop, so VC2 would be equal to V plus minus the voltage across this resistor, which is IC2 multiplied by RC. So you do the same thing for VC1. So you had this equation set here. Now plug these two equations into this equation. You can have a simplified term of VO output equal to IC1 minus IC2 multiplied by RC. Okay, now look at this here. Since we already figured out our GM, right, and we can basically relate GM to into the change in current when there's a difference introduced in the input. So let's give that as I can have my current to increase by GM multiplied by VD over 2. Okay, and here I can have my current IC2 reduced by GM multiplied by VD over 2. So if I plug these two terms into this equation, I plug this term for IC1 and I plug this term for IC2, I can have a new expression like this. In here you can see that IQ over 2 will be cancelled out, and this term and this term add up together, so it no longer be half. So now you have just a simple term of GM, VD, RC. Okay, almost done. And finally, we can have our voltage gain by divided both sides by VD. Then you can have the whole voltage gain is equal to GM multiplied by RC. So usually GM is given for each transistor around 50 milliampere per volt. Therefore, if you want to design your gain for your amplifier, you need to choose an appropriate RC. So that's it for today. Next, I will try to cover the small signal equivalent circuit.
Okay, so to sum up, you all now can basically analyze how much gain that you can design for to amplify the small difference between the two inputs. So it's just a pretty good way if you want to compare two signals that is very similar. So they just have a few millivolt difference, and you can figure out how to amplify the small differences using basically the design that I just suggested. Just change the RC. So I hope you all learned something new today, and I will see you guys next time. Bye.